Hello and welcome to our workshop presentation. Hope you stay well and enjoy this year's WISEE virtual conference and space solar power workshops. I'm Cheng from Georgia Institute of Technology. In this presentation, I would like to give a brief overview of Refset mission and its history, followed by the final results. The radio frequency tech satellite is a 3-unit CubeSat developed by undergraduate students at Northwest Northern University and Propagation Group at Georgia Tech to demonstrate distributed sensing in space using RF energy harvesting tags and backscatter communication. Davis, Julie Cox, Quentin Frederick, and Joshua Griffin. And the background is where the satellite was assembled at NU. A total of 12 undergrad students had worked on the project over the last 4 years. The students shown above are the ones who finished the project and contributed the most to the project. And here is the GT team. From right to left is Cheng, Mohammed Ahasson, Robert Collis, and Professor Gregory Durgan. And here I'd like to give you an overview of a Refset project. And first, what is the CubeSat? CubeSats are nanosatellites typically delivered to low Earth orbit as secondary payloads and used for various experiments by educational, government, and commercial entities. One or more CubeSats are typically housed in a spring-loaded dispenser that is remotely opened to release the CubeSat into orbit from a rocket or other spacecraft. A CubeSat can orbit for several years, although science missions are often much shorter and can downlink their data directly to Earth's ground station or indirectly through other satellites. And our mission objective is to test a system for developing small wireless sensor tags from the spacecraft that harvest RF energy and communicate with the spacecraft using backscatter radio. And here is a brief summary of the dimensions, weight, battery, the material used by the Refset, and how it's deployed into International Space Station, and so on. And here is the timeline of this mission. The concept of operation for Refset is that it deploys on the first day, operates for 8 weeks for sensoring, and communicate with the ground station, and then it will be shut down and deorbits after 4 years. At first, we envision the system as the figure showed on the left. We will have a RF reader and RF tag with a deployable boom between the tag and reader, which is 75 centimeter long. And the RF tag will harvest energy from the reader and backscatter the signal with the sensor data to the reader. And here is how it works. However, there were some technical difficulties we couldn't resolve in time. For example, the deployable boom failed during functional testing, and due to schedule constraints, it was removed and the tag was fixed on the side of the satellite, which is about 4 centimeters away from the radar antenna, which is still wireless but a very short distance. And there are also some other technical difficulties and schedule restraints. The IMU and Refset were removed from the tag due to their high current draw, and now the RF tag only hosts a temperature sensor. Lastly, a local high school planned to fly a temperature sensor board on Refset, However, the software was not complete in time, so the hardware is there, but it's not functional. And let's take a closer look at the subsystem in the Refset. And the Refset system is powered up every 16 hours on orbit. The payload control board, which is called the interface board, tracks time, and every 16 hours requires the NSL onboard computer to supply power to the RF reader. When the power is applied to the reader, the DSP turns on the phase lock loop, which begins transmitting, and it transmits a 5.8 GHz continuous wave. The continuous wave is transmitted for 2 minutes while the RF tag data is ignored, power off for 4 seconds, and then turn back. The DSP then began listening for RF tag data. This approach prevents a problem in receiving reliable data from the tag after. And this is the functional block diagram of the Refset that is related to the RF system. The IB board is the master control processor of the RF system payload. When it's time for the RF system to turn on and collect data, the IB communicates with the EPS and requests DC power. When powered on, the DSP turns the phase lock loop on and start transmit continuous wave signal that is both transmit to the tag and use as the LO for the down converter. The tag harvests the energy with temperature sensor and backscatter the temperature data at a rate of 125 kilobps. The received signal is direct down converted and sampled with a 12-bit ADC in the DSP, and simultaneous sampling of I and Q channel at a rate of 375 kilo sample per second. The DSP sends the samples to the IB board, which packetizes it and forward it to the global star radio for downlink. The front view of the Refset payload, which includes a 5.8 GHz continuous wave transmitter, a 5.8 GHz direct down conversion receiver. The baseband IQ waveform were simultaneously sampled using 12-bit ADC at 3 times the tag bit rate. The reader, transmitter, and receiver antennas were custom microstrip patch antennas on the common slotted substrate to reduce leakage from the transmit antenna to the receive antenna. And here is a back view of the payload. This slide shows the RF tag. The energy harvester circuit was fed by a 2-element microstrip patch antenna array. A separate microstrip patch antenna was used for backscattering communication. The energy harvester charged a supercapacitor through a power management circuit. The tag was controlled by an MSP430 microcontroller that contained a temperature sensor. The digital value from the temperature sensor controlled a RF switch that modulates the backscatter signal. I believe this was our first flight-side operation on February 8, 2019, a little bit too close to our May delivery deadline. This photo shows the integration of Refset. Before we put it together, we engrave our names in the anodized layer of the aluminum ballast. And this is the first configuration of Refset prior to delivery in Houston. And here is the launch date. This is a photo of the cargo resupply 18, CRS 18 mission from Cape Canaveral, Florida on July 25th, 2019. It's a SpaceX Falcon 9 rocket, and Refset is in the Dragon capsule on its way to the International Space Station. The team watched the launch from a building on the Canaveral Air Base about 3.5 miles from the launch pad. And here is the Dragon 18 approaching the International Space Station for docking. Dragon 18 contains Refset in its pressurized compartment. Its image shows the configuration of the ISS while Refset was stored as cargo. And here is a NASA caption of this image. A Refset is housed in the center dispenser. And then I'd like to discuss the results we gathered from this mission. The graph showed in this slide is the sampled baseband and Q waveform received from the RFTSat on orbit beginning on August 7, 2019 at 12:42. And the waveform consists of a header, 2 copies of the RFTSat temperature, and 2 copies of the burst counter. Samples that were missing on the I channel, shown in the figure on the left, were estimated using the corresponding sample from the Q channel. And the source of the missing samples is caused by both the RFTSat system and the Refset downlink radio or downlink packet lost after being transmitted from the Refset downlink radio, which is more often the case that caused the source of lost samples. This waveform has also been interpolated to increase the number of samples per bit, as shown on the right-hand side. A total of 44 valid temperature readings were recovered from the Refset data, shown in the figure here. Temperature measurements were determined to be valid if the multiple copies of the temperature bytes and burst count bytes from both channels in a single tag waveform did not contradict each other. Unfortunately, the RFTSat temperature measurement could not be correlated with other temperature sensors on the satellite because the other temperature sensors do not return data to us. However, orbit data provided by the U.S. Air Force in the form of 2 line elements were used to estimate the position of the satellite at the time of each temperature measurement. The orbit visualization tools in the system toolkit from AGI were used to estimate whether or not the sun was visible to Refset or occlude at the time of the measurement. The presence or absence of sun is indicated by the color of each bar in the figure. Although the temperature of the tag sensors is influenced by many factors beyond the presence or absence of sunlight, it does provide a very rough mean of validating the data received from the RFTSat. As you can see in the figure, higher temperature generally correlate with sunlight, while lower temperatures correlate with the absence of sunlight. Here is another plot that shows temperature measurements versus time in sunlight and darkness. You can see the correlation between temperature and sunlight much more clearly. I like that a lone outlier in the middle. That's how you know it's real data. The lessons we learned from this mission and takeaways are space missions filled with gut checks and cost overruns. The mechanical aspect of the spacecraft provided more problem than the solid-state electronics. We had a successful proof of concept despite all the difficulties we had, and we demonstrated the versatility of passive wireless sensors in space. So thank you for your attention, and please let me know if you have any questions.